Hi, today we'll talk about our work on DataProVe fully automated conformance verification between data protection policies and system architectures. Probably most of us are aware of the GDPR, which took effect in 2018, and it puts more emphasis on privacy by design, where businesses are encouraged to implement measures at an early stage of the system design phase. Motivation behind this work is that during system design, informal and manual conformance checks can be error-prone and time-consuming, especially if the system is large with a huge number of components, which may also include third-party applications. To address this, we propose a framework in which a specified system architecture can be verified against a specified privacy or data protection policy. This aims to have system designers detect any flaws at an early stage. However, we also note that our framework can be used for auditing purposes as well, verifying existing architectures and policies after the design phase. We address the architecture level, which is different from other works that verify the security of protocols or codes. Since at the architecture level, we abstract away from the low-level system implementations, such as codes, our framework is suitable for verifying large systems with high number of components, including third-party applications. I will talk about the formal definition of architectures later. So with this, we are able to verify the entire system or service instead of focusing just on a single protocol or single application. And one can use our framework to detect design flow at high level and then continue to look into protocols or application codes after that. Although in the literature there are many works in this area, they follow a different philosophy, as most of them address policy enforcement during system run. For instance, some works only address the policy level, such as how to specify privacy policies of web applications and check if the policy meets the expectation of customers. Some works address both the policy and architecture levels, but in an informal way. So basically here, the authors discuss potential directions for modeling different data protection rules, such as data access requirements and data linkability requirements, which we also address in our paper. Some focus on the policy specification approaches for the transmission of personal data and how to enforce these policies during system operations. And some focus on privacy threat modeling of system architectures, but without considering the policy level. And finally, some focus on the code level and the verification of policies against codes. And as I already mentioned, just usually focus on a single application due to the code complexity, but it would be quite challenging if someone wants to verify the entire service or system with this. Compared to just our framework follows a different philosophy. It focuses on the system design phase. It supports the formal specification of both policies and system architectures. It supports fully automated compliance verification between them. And it also supports specification and modeling of crypto primitives and operations, as well as attackers. To summarize, our main contributions include a new variant of privacy policy language which proposes syntax and semantics, a new variant of architecture language, the definition of three types of conformance, namely privacy, data protection, and functional conformance relations, a new and efficient fully automated verification engine, and a prototype implementation. In the following, we will highlight the syntax of the policy language. We don't talk about the semantics due to time limitations, but it can be found in the paper. So the privacy policy is defined on a data type. For example, a data type can be a health record or address and so on. And in our case, each policy contains 7 sub-policies for data collections, usage, data storage, deletions, transfer, data access, and link. The data collection policy requires to specify whether a collection consent is required for this type of data, which can be yes or no, and a set of collection purposes, which can be, for instance, create an account or calculate a bill, receive insurance, and so on. The usage policy is similar to the data collection policy, but with usage consent and usage purposes instead. Next, the data storage policy requires one to specify whether storage consent is required, the location of the storage, and a set of storage purposes. We define high-level locations such as decentralized or centralized options, which can be main storage or backup storage. The deletion policy includes the specification of the location from where the data can be deleted and the numerical deletion delay. So in our paper, we only consider numerical delay. The transfer policy also includes a set of entities to whom the data of this type can be transferred, such as third party, have authority, and so on. And then the last two sub-policies address data privacy and security requirements. The data access policy defines a set of entities that can access or can have the data of this type. Finally, the data link policy contains a set of pairs, which defines who can link a piece of data of type theta with the data type defined in the pair. For instance, have authority is allowed to link an address with data of type theta. So if the theta, for instance, is the health record, then the authority can link someone's address with someone's health record. Now, as for the formal definition of architectures, we define architecture as a set of actions which define who can do what in the system. So, for instance, in this picture, action calculate at says that in the system, an entity E can calculate a piece of data of type theta. This is denoted by x theta here at some non-specific time, which is denoted by time tt in this case. Similarly, receive at denotes or specify that E can receive the data x theta at some non-specific time. Okay, so the rest actions can be interpreted in the same way. Here we can see an example of smart metering architecture with 5 entities and 2 actions. So in this case, the server at the service provider's side can receive an energy record of gas and electric consumptions from a smart meter. Which is then can be centrally stored in the main storage. We define 3 conformance relations between a privacy policy and an architecture. The privacy conformance relation says that if in a policy an entity E does not have the right to access any data of type theta, then E cannot have this type of data in the corresponding architecture. Similarly for the data link requirement. The data protection conformance deals with the consent collection requirements, the purposes, the data transfer and data deletion requirements. And finally, functional conformance addresses the functionality of a service that it can or cannot provide. The automated verification algorithm is based on logic resolution and inference rules. For example, for privacy requirement, we define a set of inference rules to capture what are the conditions for an entity to have a piece of data. We also define rules for data protection and functional conformance, as well as for data link requirements, but due to time limitations, we don't talk about them here. In the verification process, the policy and sub-policy on the left side are mapped to logical goals to be proven, while the architecture actions on the right side are mapped to logical facts with which we attempt to prove the goal with the use of the inference rules. The proof process can be modeled by a derivation tree, which either finds a proof or not. We note that the algorithm only returns one positive proof, even if there are many. If no proof is found up to a given boundary, then it stops. So basically means that the solution is only complete up to a predefined boundary. We implemented a prototype tool based on the proposed theoretical approaches, which is available online on GitHub, as you can see. As an example, in the paper, we demonstrate the feasibility of our approach and tool by verifying two contact tracing approaches, DP3T, which is a decentralized approach, and PEP-PT, which is a centralized approach. We note that the tool can be used for any kind of services and system. We only took this example here because it's timely and relevant. For demonstration purposes, we define a common policy for both architectures, which includes policies such as short-term IDs and long-term IDs of phones must be stored in a decentralized way in phones. The backend server has no right to link short-term IDs and long-term IDs with each other, and the phones must delete the short-term IDs within 14 days. After running the verification against DP3T, we identified only functional compliance issues related to the functionality of the service, such as health authority cannot have statistics about the global cases. In the case of PEP-PT, we find some privacy compliance issues, such as the backend server can link short-term and long-term IDs with each other, or the short-term IDs of phones are stored until 21 days, but only 14 days are allowed in the specified policy. In general, the performance of the tool is quite good, and it depends strongly on the data length or the number of arguments in the data. For instance, a document can contain several pieces of personal data as arguments. And it also depends on the number of architectural actions. To conclude, we propose a novel framework and tool to automatically verify compliance between policies and architectures, which could be used for system design, auditing, or educational purposes. In the future, we plan to improve and extend the framework and address some limitations, such as supporting also non-numerical delay. We change the policy language to support conditional requirements, other types of legal basis of processing, and considering special category data as well. Thank you for your attention, and I'm happy to answer any questions. Thank you.